Hi, my name is Wes Bateman. I'm a consulting security engineer out of the commercial West area, and I'm here to talk to you today about Cisco's next generation IPS offerings. This is the design module for the NGIPS track, and today I'll be talking about the product design, effectively the hardware and software components that make up the NGIPS system, and solution design, the rules of thumb for sizing and building a bill of materials for your customers and helping to design and architect a solution. At the end of this module, you should have an understanding of the firepower appliances and the software components of the NGIPS system. You should also be able to utilize various sizing guidelines that will be provided to help you scope and size a deployment. We'll start our discussion with the overall product design of the Firepower Next Generation IPS system. The various components that comprise a firepower deployment are depicted in the slide. Note at the top that a Firesite Management Center is required for a next generation IPS deployment. This system, formerly called a defense center, can be deployed as either a physical or virtual appliance. There is an option for certain models of the physical Firesite management appliances for running a redundant pair in a high availability configuration. The Firesite Manager centrally controls all configuration, updates, and other administrative tasks for all of the managed firepower appliances in a deployment. It also receives all eventing data back from those systems and is the central correlation and analysis center for a deployment. The Firesite Manager will communicate with the Cisco Talos Threat Research Group's collective security intelligence cloud properties to keep current with the latest intelligence and threat data. This back-end threat research capability is a key feature to highlight with customers, as Cisco's capabilities in this space are a huge competitive advantage and really feed the efficacy of all of our security portfolio. This collective security intelligence is one of the main reasons that Cisco security fares so well in independent third-party testing, such as NSS Labs testing of next-generation IPS systems as well as other tested technologies. Note the FireAMP, or Advanced Malware Protection for Endpoints, oval on the slide. AMP stands for Advanced Malware Protection. The AMP for endpoint clients all log their data to a cloud destination, but this diagram is representing the fact that the Firesite Manager can consume this endpoint malware data from the cloud and correlate it with all of the data it directly collects from the network firepower systems. The firepower appliances, both physical and virtual, shown at the bottom, provide several capabilities that are critical to the NGIPS system's operation. First, the base contextual awareness layer is key because it underpins what makes the firepower system so special. A pair of technologies released by SourceFire back in 2004 called RNA for real-time network awareness and RUA for real-time user awareness are now collectively called Firesite. And that's where the system passively and in real time profiles host traffic and builds a network map of the environment being defended. It populates this map with data on each host's operating system and version, as well as client and server applications and versions thereof in use on each host. Further, it includes logged-in user data for each host and can then map all of this passively collected intelligence back to known security vulnerabilities that the system has protections available for. This enables recommended rules or automated IPS rule tuning, as well as impact flag analysis, whereby the system triages intrusion events and categorizes them with different impact flags to indicate the actual potential for a given host to be impacted by a detected threat event. These automation capabilities are huge differentiators for us, and they can save security teams countless hours as well as help to ensure that their time and attention is appropriately focused on the threats that actually matter in their unique environments. This contextual awareness is really what transforms our Snort Engine's intrusion detection and intrusion prevention capabilities into next-generation IDS and next-generation IPS capabilities. In addition to the Snort Engine doing deep packet inspection to find threat, since it's not depicted elsewhere in this diagram, I'll just point out that the system can also perform what we call security intelligence, effectively providing optional alerting and/or blocking of connections based upon the reputation of the remote IP address. Enhancements to security intelligence are scheduled to be released in version 6 that will extend the reputational checks beyond IP addresses to hosts and domains as well. The platform also can offer application control. Since it already has application awareness, this can be leveraged in the access control policies to provide rich application control capabilities. Although it is out of scope of this track, I'll briefly mention that the firepower appliances can provide NATing, switching, and routing, and act as NGFW platforms in and of themselves. Although in most circumstances you'll be better off positioning ASA with firepower services for such needs, as the ASA is much more mature and featureful when it comes to NAT, routing, VPN, high availability and clustering options, etc. Finally, network-based advanced malware protection, as was touched on in the endpoint AMP conversation a few moments ago, is provided by the system as Snort's various preprocessors can help identify file transfers in various protocols, and we can then carve those files out of the traffic streams and provide control over file movements, and AMP capabilities such as malware, cloud lookups, and dynamic analysis of files can be brought to bear. So as we start to visualize traffic going through the firepower system from a software and policy perspective, effectively the network discovery policy is hit first, and we look for opportunities to supplement our network map with new discovery event data. Next, we proceed into the access control policies domain, where an access control rule match will dictate what type of intrusion policy, file and malware policy inspections, and also what kind of event logging to perform. That will all be determined with that access control policy rule match. Access control policies also leverage security intelligence reputation data, as well as URL and geolocation or GeoIP information. As we peer more deeply into how the system does all of this, let's talk about the physical interfaces and the traffic flow, or the quote-unquote life of a packet within the system. The physical firepower appliances have sensing interfaces that can be used for passive inspection, or they can be paired into transparent Layer 2 bridge inline sets for a bump-in-the-wire deployment. Additionally, the system's interfaces can also be configured in routing mode, and traffic traversing between routed hops can also be inspected. The interfaces are fixed on the 7000 series appliances, with some chassis models offering a choice between 1 gigabit per second copper or 1 gigabit per second fiber. The 7125 and 7150 appliances have 4 ports of 1 gigabit per second copper interfaces, but they also have 8 SFP bays which can accommodate additional interfaces. Note, though, on these that the added interfaces do not have fail-open or fail-closed configurable bypass switching capabilities, like the built-in 4 ports in those systems. Also, note that all of the ports on the rest of the 7000 series appliances have built-in bypass switching capabilities as well. That bypass switching is configurable, and the systems can be configured to fail open or fail closed, depending on the needs of a given deployment. The 8000 series appliances introduce network modules, commonly just referred to as netmods. Those provide the ability to install 1 gigabit per second copper or 1 gigabit per second fiber netmods, 10 gigabit per second fiber netmods, and 40 gigabit per second fiber netmods. These physical sensing interfaces then feed into dedicated network flow engine cards, or NFEs. The NFEs provide load balancing of traffic flows across many Snort instances to help scale performance. The NFEs can perform layer 2 through 4 inspection and provide extremely fast treatment of traffic while it is within the NFE. As traffic that requires additional inspection leaves the NFE, it is sent to the Data Acquisition Module, or the DAQ. Then, various preprocessors are employed in order to normalize the traffic being inspected. This helps to ensure proper inspection of traffic and helps to combat attempts to evade detection. The access control rules, as previously discussed, come next, and if the traffic is to be immediately blocked or trusted without further inspection, also referred to as fast pathing, this verdict can be returned to the NFE where the blocking will take place, or, in the case of trusted traffic, where the flow will be promoted into the hardware-accelerated NFE layer for all future handling without exiting down into the DAC and other subsystems. If the traffic needs to be subjected to further scrutiny first, then it continues along the path as prescribed by the access control rule before a verdict is returned to the NFE for final disposition. This single-pass engine architecture allows for extremely fast processing of traffic with minimal introduction of latency. To that point, actually, latency alarm thresholds will be hit if traffic is ever held for over 150 microseconds, so that should be a rare event. In most cases, you should expect less than 1/10 of a millisecond of latency introduced by the system. Latency is dependent upon many variables, but I only raise this here because I've been asked about it by many customers, and in fact it is very rarely even detectable, let alone an issue in a properly sized deployment. As file policies are configured, just as a point of information, please note that the various protocols inside of which you want to inspect for file transfers will result in automatic enablement of preprocessors for those protocols. This can have performance implications, so just be aware of that fact if maximum system performance is required in a given deployment. A couple of additional points about the physical dedicated firepower appliances. Depicted here is an 8200 or an 8300 2RU appliance. These appliances have multiple netmod bays, which we'll describe in more detail shortly, along with more information about configurable bypass interfaces and device stacking options. Also, firepower appliances provide an LCD to allow for headless configuration. Note that this can be disabled in shops where the potential security implications of that ability are not acceptable. Even in that case, however, the LCD can still provide useful system data at a glance. The firepower systems all provide lights-out management capabilities, leverage solid-state drives for better reliability, and provide hardware acceleration capabilities, already discussed. The final topic I'll cover today from a product design perspective is the availability of virtual appliances, both for firepower next-gen IDS and IPS sensors, as well as for Firesite Management Center appliances. These appliances all will only run within a VMware hypervisor environment today. That may change in the future, so at the time you view this, you may want to confirm the latest information on hypervisor support. The virtual sensing appliances are probably most commonly deployed in passive or IDS mode when used in production by most customers in the field, but they can act as transparent bridges inspecting traffic moving through two vSwitches. These appliances are often appreciated for their ability to view traffic between virtual systems that never leaves the virtualized environment and therefore would never be seen on the physical network by other firepower systems. The virtual Firesite Management Centers can manage up to 25 total sensors, regardless of whether or not the managed systems are physical or virtual firepower appliances, firepower services modules on ASAs, or any combination of those. The virtual Firesite managers are very popular in the commercial segment due to their lower cost and the ease and speed with which they can typically be deployed. For deployments that require high availability of the Firesite managers, or that have more than 25 devices to manage, or that expect large numbers of event data flows to come back to the Firesite managers, in those cases, the physical Firesite management appliances are the most appropriate. Now we move on to solution design. Here I provide a relatively common use case that you may observe in the field. For this example, let's assume that we have a customer with existing perimeter firewalls who would like to inspect ingress and egress traffic more granularly by leveraging the Firepower Next Generation Intrusion Prevention System capabilities. We see this kind of scenario often behind firewalls that cannot run advanced threat protection capabilities or whose threat protection capabilities are deemed by the customer to be substandard. Typically, this conclusion is arrived at after some coaching from us and after they see what the firepower system can do. These existing perimeter devices could be a different vendor's firewalls, or perhaps basic routing appliances, or other devices, or they could very well be a generation of ASA appliances that do not support firepower services. At this point, we have a legitimate use case, but it's always a good practice to learn the customer's actual business drivers. What is causing them to consider investing in this additional layer of advanced threat protection? Are they able to articulate desired business outcomes? I'm embarrassed to toss around buzzwords like this, but the reality is that we have a very compelling solution and many technical InfoSec practitioners simply like it and want to look at it, learn about it, and possibly play with it in an evaluation type of scenario. In order to protect your time and our overall sales resources, identifying whether or not an opportunity is properly qualified is critical. This is one of the reasons we do not engage in evaluations or proof of concept exercises, but rather what we call proof of value engagements, which will be covered in more detail in a separate module. Some common business drivers we see are customers who come to us after having suffered a security incident, or perhaps they're subject to new or changing compliance requirements, or perhaps their threat detection and protection capabilities were found wanting during an audit. Whatever their drivers may be, if a next-generation intrusion detection or prevention system can help them achieve their desired business outcomes, then we need to start to investigate how we can architect a solution to do so. We need to determine which segments or places in the network need to be inspected and how. Will we be in an inline, active IPS deployment, or will some or all of the segments be passive IDS monitoring only? We need to consider features we need to enable to meet the required outcomes, and then the amounts of traffic we need to inspect with the firepower system's various features and capabilities. This will then help us determine which types of firepower systems are most appropriate from a capacity and port density perspective. The last real piece is scoping out appropriate Firesite Management Center devices. Firepower appliances are deployed in the smallest branch offices all the way up to large campus networks and data centers. Traditionally, IDS and IPS systems have been found monitoring network perimeters. This would typically include end-user traffic egressing out to the Internet, and Internet traffic inbound into DMZ segments housing public-facing servers. As time has gone on and threats have become more advanced, however, we've found organizations requiring more and more visibility, adding inspection to their most business-critical internal-only facing systems, inspection to B2B partner extranets, to WAN links between company sites, and increasingly toward wanting to monitor east and west traffic within data centers and even between end users where practical. All of that said, though, your most common deployments are still at the perimeter, which is in line with our example use case. Wherever the need turns out to be, there are firepower appliances to meet that need, from the smallest 7010 appliances providing 50 megabits per second of IPS inspection in the smallest of offices, all the way up to the 8390 systems capable of 60 gigabits per second of IPS inspection and appropriate in large data centers. This slide helps with visualizing the appliance line and which systems have modular interfaces and which systems can be stacked. Note that all of the IPS throughput numbers are for IPS inspection only. Later, we will discuss performance implications of application visibility and the Firesite contextual awareness capabilities, as well as that of advanced malware inspection of network traffic and other features. Continuing our exploration of the appliance options available to our customers, let's take a closer look at the firepower appliance model lines available and their features and capabilities. We already briefly covered some firepower appliance features that are universal to all models. Here we have an overview of the various lines, restating the universal features found in all appliances, and specifics found in the 8000 series, the 7100 series, the 7000 series, and more. The 8000 series appliances all have modular netmod bays, and some of the models are stackable to allow for additional throughput capacity. The 8100 series are 1 RU in height, and the 8250s and 8350s are both 2 RU or rack units in height. The 8260, 8270, 8290, as well as the 8360, 8370, and 8390 are all stacked 8250s or 8350s, so they consume 4, 6, or 8 rack units of space. More about stacking in the slides to follow. The 7000 series, including the 7010, 7020, and 7030 appliances, all are 1/2 width, 1 rack unit boxes. They have 8 fixed 1 gigabit per second copper interfaces, all with built-in configurable bypass capability. There is a shelf kit available that allows for mounting of 1 or 2 of these 7000 series systems into a standard network rack, consuming 1 rack unit of space. The 7100 series have 8 1 gig fixed ports. They are made in both copper and fiber models, so you have 8 ports of 1 gigabit copper or 8 ports of 1 gigabit fiber. That is to say that all 8 of the 1 gigabit per second fixed ports can be of copper or fiber. These ports also all have configurable bypass capabilities built in. The 7115, 7125, and the 7150 amp appliance all have 4 fixed ports of 1 gig copper with built-in configurable bypass capabilities, as well as 8 additional SFP bays. The SFP interfaces do not have configurable bypass capabilities. The 7115 and 7125 appliances were originally more designed around a firepower appliance next-generation firewall use case, and the 7150 amp appliance was built around a malware appliance use case and is based upon the 7125 chassis, just with additional hardware capabilities to assist it with performance under the demands of network amp activities. Back to the stacking options for the 8000 series. The 8120, 8130, and the AMP 8050 and 8150 appliances cannot be stacked. We see here, however, that the 1 rack unit 8140 model can be stacked one time for 2 8140s together, taking 2 rack units of space and delivering 12 gigabits per second of IPS inspection instead of the 6 gigabits per second inspection provided by a single 8140 chassis. Note that this stacking works in a manner where the base chassis is the controller of the stack and the additional stacking module or modules are only adding compute power. The 8250 and 8350 systems provide 10 gigabits per second and 15 gigabits per second, respectively, of IPS inspection throughput. The 8350 is effectively a hardware refresh of the 8250, and while both were offered for sale simultaneously, for all intents and purposes, the 8350 has and should replace the use of 8250s in the field. The 8250 or 8350 can be separately purchased, and then, when needed, additional units can be added to increase capacity. Unlike the 8140 though, 8250 and 8350 stacks can be purchased pre-stacked. In other words, the 8260 and 8360 are 2-unit stacks, the 8270 and 8370 are 3-unit stacks, and the 8290 and 8390 are 4-unit stacks. A stacking kit is required for each unit stacked, which consumes one netmod bay in the base chassis for each additional unit stacked onto it. The netmod bays on the added units are not used except for one to accommodate a stacking network module to connect it to the base chassis. So, this means that when stacking, as throughput capacity increases, available port density decreases. You'll see this visually depicted in the next two slides. Here we see that the 8140, a one-rack unit system, has 3 network module bays available for population with sensing interface netmods. The 8250 and 8350, the 2-rack unit chassis, have 7 total network module bays. The 8250 and 8350, the 2-rack unit chassis, have 7 total network module bays. If you are just adding sensing interfaces, the netmods have 2 or 4 interfaces each. More on the netmod options in a moment. So if you populate all 7 netmod bays in an 8350, for example, you could have up to 28 total ports available on that system. Stacking impacts this, though. As we stack units, we lose netmod bays that can be used for sensing interfaces. The upper left of this slide shows how a single 8140 has 3 netmod bays available, for up to a total possible of 12 interfaces, if all netmods used were 4-port varieties. If we stack it, though, with the one additional unit that it can support, we have only 2 netmod bays left for use with sensing interface modules. In the lower left, we see again how an 8250 or 8350 is 2 rack units tall and can accommodate up to 7 netmods. As we stack, though, a 2-unit stack can only accommodate up to 6 netmods, a 3-unit stack up to 5, and a fully built-out 4-unit stack can only accommodate up to 4 netmods, maximum for sensing interfaces. So an 8290 or 8390 can only have up to 16 total possible interfaces, in other words, 4 each of 4-port interface netmods, while a base 8250 or 8350 can have up to a total of 28. You can see here that there is a bezel covering all additional network module bays for the stacking units. If you order additional units for stacking, they will come like this. Now let's look more closely at what netmod options are available. You can see all of the netmod options in the table to the right on this slide. The non-bypass network modules primarily came out for next-gen firewall use cases, but note that there is a higher port density for the 4-port non-bypass 10 gig netmods than you can get with a single 10 gig netmod that does have configurable bypass capability built in. The bypass switch on the 10 gig netmod especially takes up quite a bit of physical space if you ever see one out of the chassis, so the port density is lower on those modules. The list price is the same, however, so in deployments where any links don't require the configurable bypass capability but does require 10 gigs, you may be able to achieve more desired ports if required for the same price. Netmods of different types may be mixed on a single platform if desired. As noted here, all interfaces support link state propagation so that if link is lost on one interface, it can propagate that link state change to the other interface in the inline pair. Note too that the 40 gigabit per second modules are only available in a configurable bypass type. They are actually 2 rack units tall themselves, consuming 2 netmod bays vertically, and as such are only supported on the 2 rack unit 8250 and 8350 chassis. The use of 40 gig netmods requires a 40 gig NMSB switch module in an 8250 or 8350, or in the base chassis in a stack of such units. This switch is already included in the 8270 and 8290 and all of the 8300 stacks, meaning the 8360, 8370, and 8390, all of which are 40 gig capable as they ship. The 8250, 8260, and the base 8350 units do not include this switch by default, so if you're adding 40 gig netmods to such units after purchase, it will be necessary to order one of these NMSBs for each chassis or stack. This slide also depicts the two slots in which the 40 gig netmods can be inserted into a 2RU 8200 or 8300 chassis. So the rough guidelines provided on this slide are extremely useful for a quick sizing estimate. The next slide contains some information about a performance estimator tool that is now available, which provides much more accurate and scientific sizing guidance. The rules on this slide give you some granular and relatively accurate ways to estimate conservative performance numbers in the field. To give yourself a very quick and basic estimate though, you can generally take any firepower appliances, excluding the AMP appliances, more about those in a moment, and take their rated IPS inspection throughput capacity, and if you're just doing IPS and no app visibility or control, or just doing app visibility and control and no IPS, then in many cases that rated number, that original IPS-only number, is the correct one to use. If you run both AVC, or app visibility and control, and IPS together, which is the most common deployment, then you should cut that number roughly in half. Some people may say 6/10 or 2/3 of IPS-only rated performance, but it's safer and easier to just say 1/2. Then, if you turn on network AMP in addition to app visibility and control plus IPS, then take about 1/3 of the original rated performance. This may be quicker to do rather than calculate the type of app visibility you're performing, etc. It's a great, quick, and easy guideline that's pretty conservative. Some of the newer hardware will outperform those estimates by a fair margin, but you shouldn't get stuck too undersized for the most part doing it this way. Now, as noted here for the AMP appliances, including the 7150 and 8150 and the newer 8050, the rated performance numbers are calculated already anticipating running of app visibility and control, and IPS and AMP, and even URL filtering, effectively all inspection features. Connection logging and other configuration choices can still impact these boxes to the point that they may not hit their rated performance numbers, but most configurations should be able to achieve the rated numbers with all security features enabled. This makes sizing with these systems very simple and straightforward. This is a screenshot of the web-based performance estimator tool. It has many checkboxes you can employ to much more accurately define a use case's needs and get resulting performance data back for appliances based upon actual testing numbers. This is the best way to go if you need to accurately size and perhaps push the system a bit more because of budget or other constraints. This tool requires you be granted access. That's as simple as joining an internal mailing list. More about that in the resources slide near the end of this module. When it comes to sizing appropriate Firesite management centers, these are the primary hardware options. There is also a hardware Firesite 750, but it is not shown here as it is extremely small, and in pretty much any production setting I would strongly advise you go with a virtual Firesite management center or a Firesite 1500 or 2000 system instead. The Firesite 1500 and 3500 models are being refreshed basically with the 2000 and 4000 models, which are based upon UCS hardware. From a sizing perspective, the virtual Firesite Manager can manage up to a maximum of 25 devices and store 50,000 hosts and 50,000 users in its network map. Its maximum events or flows per second rate varies with the capabilities of the virtual infrastructure upon which it's hosted. It most closely resembles the Firesite 1500, but costs quite a bit less, making it a very attractive option for many customers. Where high availability is required, or more managed devices or more events per second are needed, then the models shown here are appropriate. For the most part, customers will be better off with the Firesite 2000 over the Firesite 1500 and the Firesite 4000 over the Firesite 3500 until those older appliances go end of sale. Total event storage is listed here, but in reality, the key sizing stats for each system really revolve around total number of managed devices supported, maximum hosts and users in the network map, and maximum events per second that the system can insert into the database. Here I've taken our initial sample customer use case framework and have fleshed it out with some answers to the questions we posed earlier in this module. If we had discovered these use case requirements from our customer, we could then leverage the understanding we have of sizing guidance to be able to scope out appropriate items for a bill of materials for this customer's needs. We identified 1.5 gigabits per second of inspected throughput In order to understand which appliances are right, we also have the added requirement that we run AVC, App Visibility and Control, as well as IPS, and also we'll be running Network AMP. Due to this, rather than try to take perhaps an 8140 and figure 1/3 of the 6 gigabits per second of IPS inspection, which would work here, it's probably easiest and most cost-effective in this case to leverage a dedicated AMP appliance. The 8150 is quite appropriate here, providing 2 gigabits per second of inspected throughput with all features enabled, which suffices for our needs and gives us some modest room for growth. The customer indicated 2 inline sets, which require 2 interfaces each for a total of 4. Then also, the passive link will require a single interface, so a total of 5 copper 1 gigabit per second interfaces are required, so 2 4-port copper net mods for a total of 8 ports. 3 will remain unused for future growth. It was not specifically noted, but generally the configurable bypass net mods are advisable if there is not a specific reason to use non-bypass net mods. Since we're behind a pair of firewalls, we'll spec out 2 appliances, one behind each firewall, giving us redundancy as well, in a manner that does not compromise the redundancy the customer has already built into their architecture. The customer does not require high availability for the Firesite Manager console and indicated that a VMware hypervisor environment did exist. This will be a cost-effective choice and should not have an issue handling 2 devices in most circumstances. The Firepower Services subscription licensing, in this case, needs TAM. This includes T, which, as in Tango, which stands for threat, which gives you the IPS capability, A as in alpha, which stands for App Visibility and Control, and M as in Mike for malware or AMP. There is also an option for C as in Charlie, which was left out, which basically stands for content or URL filtering capability. As we close out this module, here are some additional resources that you can use for reference information and also to access the Performance Estimator tool. The user guides are extremely comprehensive, so any future questions that may arise may well be readily answered by searching the most current user guide. Also note that access to the Performance Estimator tool is controlled, and to be granted access, you must join the appropriate mailer list. The list name and the link to the mailer tool are also provided here for your convenience. Now that we have completed this module, you should be able to list the core feature technologies that run on Firepower physical and virtual appliances. You should be able to describe the various appliance models available and be able to leverage sizing guidance to appropriately scope out a deployment for a given customer use case. Thank you very much for your time. I hope that you've found this module to be helpful as an informative piece on NGIPS design. Take care.